The next thing we're going to do is very much related to what we just did, just opposite. So what we did before was we had the sine or the cos of an angle, and then we had to write it out as a sum and difference identity. What you're going to do here is recognize that something is a sum or difference identity and then write it back as a single trig function. So for example, if you look at this one, I can't evaluate the sine of 70 and the cos of 20 without a calculator, but maybe you recognize this goes sine, cos, cos, sine, and it makes you think of your identities. Sine, cos, cos, sine. And then whatever sign is in the middle, right, is the sign that goes in your sum or difference. So for this one would be a sum sine identity. So I'm going to write this as the sine of 70 plus 20 degrees, which is now the sine of 90 degrees, which is one of my special angles. The sine of 90, when you're evaluating it, remember from chapter 6, you have two options. One, you can think of sine following y, because sine of theta is opposite of it over adjacent, or y over r. So for 90 degrees, it's a 0.01. So the y value is 1 and the r value is always 1. So the sine of 90 degrees would be 1. Another way, now that we've finished chapter 6, is that if you're really comfortable with a graph of a sine curve, you could look at a sine curve and be like, your first key point would be at pi by 2, and it would be a value of 1. So you now have two ways of evaluating the sine of 90. All right, this next one you could actually do as written, but they want you to evaluate it as a single angle. So I want you to recognize that it goes cos, cos, sine, sine. So this time we're looking at our cos sum and difference identities, and then whatever sign's here, you go the opposite. So since this one is a cos identity, I'm going to write cos. My two angles are pi by 6 and pi by 3. And then for this one, it's always the opposite sign. Now, hard skill, but we have to add or subtract. So I'm going to change these both to a denominator of 6. So I'm going to multiply this guy by 2 over 2, and I get minus 2 pi by 6, which means I'm evaluating the cos of negative pi by 6. How do I do that? Well, I draw a special triangle in quadrant 4 because I'm reading in a clockwise direction with a reference angle of pi by 6, and that's my 1, 2, root 3 triangle, right? Because pi by 6 is 30 degrees. It's my smaller angle, so it gets the 1 across from it. And then is anything negative? Yep, this y value would be negative because it's in a downward direction. So if I'm finding the cos of negative pi by 6, it's adjacent over hypotenuse, or x over r, and it would be positive root 3 over 2. And you can double check your signs, right? You know that in quadrant 4, cos always evaluates as positive. All right, you can always pause the video and give this one a go, or stay with me. Now, tan I do not have memorized, but I know that it's written something funky like this. So we're going to look at our tan sum and difference identities. So what I notice is that if it's a plus on top, you get a plus in your formula. If it's a minus on top, you get a minus in your formula. Okay, so it's a minus. So this is going to be the tan of 35 degrees minus 12 degrees. What is that? Well, it's the tan of 23 degrees. Now, up until now, it's been really awesome that every single one they gave us worked out to be this beautiful special triangle and a special angle that we know. Tan 23 is not. So all of a sudden you feel like you've done something wrong, which is why I put this one in here. Because if you look at the back of the book, when it comes out as an angle that we do not know, you're allowed to just touch your calculator and then you answer to 4 decimal places. So I'm going to plug in the tan of 23, and I get 0.4245. And I kind of like it because it's all kind of reminders of chapter 6 for what's going to be coming up a little bit later in chapter 7.